Welcome back. Today we're going to be talking about section 5.1, fundamental identity. So here is what generally happens in math. You go through geometry, you learn the concept of proofs. A lot of students don't latch on to that, and a lot of students kind of get this general feeling of like, I don't like proofs. It's too open-ended. I don't really get it. I don't like, what am I supposed to write? And so teachers try a bunch of different strategies to get you to the point where you can take the statement and prove that it's true. It works sometimes, a lot of times it doesn't work. What's my goal? For this section, I'm introducing you to the concept of what does it mean to do a trig proof, and what are the things that we are looking at. I'm going to give you a identity sheet, and it's got all of the things that are true. And the things you need to remember about the statements on this sheet are, like when it says that tangent is equal to sine over cosine, that's true. And this is a game of substitutions. So can I take what this is, can I pull it out and put something else in its place? To the end that I've got something that's true at the end, a statement that's still true that proves what I want to prove. And so we're going to start out with something that we know, something that we've already kind of looked at this year. It's a proof of the Pythagorean Theorem. And so one of the the most basic Pythagorean identity looks like this. I'm going to write it in green. It is sine squared theta plus cosine squared theta is equal to 1. Okay, so if I look on my sheet here, here's my Pythagorean identities. I don't know if you can see this. So sine squared theta plus cosine squared theta equals 1. And then there's some variations of it. Tangent squared plus 1 equals secant squared, and 1 plus cotangent is equal to cosecant squared. So we're going to prove that this is true. And so after this, anytime you see a 1 in a problem, you can substitute it for sine squared plus cosine squared. Or anytime you see a sine squared plus cosine squared, you can substitute in a 1. Well, what does this look like? Let's start with the unit circle. And just so you know, it didn't go away. Okay? And if I draw in just any angle, okay, any angle in standard position, because this is the unit circle, that means that this hypotenuse is 1. If I draw in this 90-degree triangle right here, this right triangle, what are the coordinates of this point? Well, we determined last chapter that its coordinates were cosine theta comma sine theta, which means that its x value is cosine theta and its y value is sine theta. I want you to think about the Pythagorean theorem for a minute. The Pythagorean theorem is a squared plus b squared is equal to c squared, or leg squared plus leg squared equals hypotenuse squared. What would that mean for this right triangle? Well, that would mean that cosine squared theta plus sine squared theta is equal to 1 squared. And you're like, Mr. Sayers, I don't know what cosine squared is. What does that mean? Well, cosine squared literally just means cosine theta squared. That's the length of this side, right here. Square it. Plus sine theta squared equals hypotenuse squared, 1 squared. The way to write this is sine squared theta. Okay, that's how we write that. It eliminates some parentheses and makes sure that we don't have just this redundant, like, because otherwise it'd be like this. Parentheses. Cosine parentheses theta parentheses squared. Look at all those parentheses. So the way that we write that is we write cosine squared theta. Okay, so that's a little sidebar. How do we get these other identities? So if you can see on the sheet, I have all these like alternate identities that are also true. Well, what we can do is, this is an equation, and we can do some things. We can manipulate it. And so now that I know that cosine squared theta plus sine squared theta equals 1 is true, because I proved it. I just showed you that this works. I can do a couple things. The first thing I'm going to do is I am going to divide by cosine squared theta. Well, how would you know to do this? You don't. I'm doing it because it's possible. In an equation, you can do the same thing to both sides. You wouldn't have any problem with me saying, oh, I'm going to subtract 3 from both sides. Same way, I'm going to divide by cosine squared on both sides. What does that do for me? Well, this gives me 1 sine squared over cosine squared. Well, remember, sine theta over cosine theta is equal to tangent, right? Well, sine squared over cosine squared is going to be tangent squared. And 1 over cosine, check it out right here, 1 over cosine squared, well, 1 over cosine is equal to secant, right? So this would be secant squared theta. Well, look at this. All I did was a simple division by cosine squared. And now I have two theorems that are true, right? So these are both Pythagorean identities. Here are my Pythagorean identities. I'm going to put them in pink box. Here's one. Here's one. They are variations of the same thing. Cosine squared plus sine squared equals 1. Two variations of it are present here, or one variation and the original. So let's say I started out with cosine squared theta plus sine squared theta equals 1 again. And instead of dividing by cosine squared, I'm going to divide by sine squared. How would I know to do this? Well, what I'm telling you is you can do it because you can do it. You can do it because it's an equation. You can do the same thing to both sides. I am forcing and manipulating these equations to make alternate versions. So cosine squared, so in the same way up here, sine over cosine was tangent. Cosine over sine is cotangent squared theta. Plus, this is 1 is equal to 1 over cosine was secant. 1 over sine is cosecant. There's my other Pythagorean identity. Boom, right there. Check it out on my sheet. How many Pythagorean identities do we have? Boom, 3 of them. Hopefully that's not too close. 3 Pythagorean identities. All of these are true. So now, anytime you see a secant squared, boom, you can put in a 1 plus tangent squared. Anytime you see a cosecant squared, boom, you can put in a cotangent plus 1. So how do we do this? How are we going to use this? Well, there's a couple ways to solve these problems. That's the beauty of proofs, is I love them so much because there's so many ways to do them. This is a problem you don't even need proofs for. You don't need trig identities. You don't need proofs. You can do this using reference triangles, but I'm going to use this as a segue. So we're going to say, hey, I could do this using reference triangles, but we're going to use identities to help us out here. So let's look. This means, so if sine theta, find sine theta and cosine theta if tangent theta equals 5 and the cosine is less than 0. So tangent theta is equal to 5. Well, what does that mean? Well, that means that I need to use some identity that involves tangent. We'll take a look here. I have one, right? Where's a tangent? Oh, here's one. So 1 plus tangent squared theta is equal to secant squared theta. Mr. Saris, how would I know to use this? Well, think about this for a second. Use something you have and incorporate an unknown that you want. Look at this. I have tangent. 1 plus tangent squared. Watch this. 1 plus 5 squared. Well, check it out. All of a sudden, that's all numbers. That's actually really nice. Incorporate something you want. Secant squared. What is secant squared? Oh, yes, it's 1 over cosine. Well, look at what I need. Cosine. So, is equal to 1 over cosine squared theta. Check this out. Therefore, secant squared theta equals 26. Okay, I just kind of rewrote it. 1 plus tangent squared. So 1 plus 5 squared is 26. So is equal to secant squared. If I take the square root, because remember that's just secant squared. So I take the square root. So that means secant theta is equal to root 26. Which means that 1 over cosine is equal to root 26. Therefore, cosine of theta is equal to 1 over root 26, the reciprocal. Okay? That's it. I have to consider the other piece now. Look what happened right here. I took the square root. So this is actually plus or minus root 26. So this has got to be plus or minus. So this has got to be plus or minus. Well, if my cosine is greater than 0, then that means that cosine is equal to 1 over root 26. What about sine? Okay, so sine is going to help. We're gonna work a little bit on this. And so I can say cosine squared theta plus sine squared theta is equal to 1. Where did I get this? Why am I using this? Well, think about it for a second. You have got to use something you know and incorporate something you don't know. Well, I have cosine squared theta. Check it out. Here it is right here. Shh, I pointed to the screen. I've got 1 over root 26 squared plus sine squared theta is equal to 1. Well, look, something I know, something I don't know. So this is 1 over 26 plus sine squared theta is equal to 1. And I'm going to subtract 1 over 26. Mr. Saris, what are you doing? I'm solving this like an equation. Sine squared theta is equal to 26 over 26 minus 1 over 26. I converted 1 to a fraction. Sine squared theta is equal to, let's see, 25 over 26. So I take square root. So sine theta is equal to 5 over root 26. Okay, so 5 over root 26 is, and this should be plus or minus, right? Because I took the square root. And if I have plus or minus root 26, how do I know what my sine is? It's plus or minus. And so therefore, it's either way. Okay? And so if my tangent, okay, so tangent is 5, my sine is going to be 5 over root 26. Okay? Could have done that with reference triangles. Tried to segue you into identities by using something that you already knew. Let's look at another one. And so in this one, we've got the cosine is equal to 0.34. Find the sine of theta minus pi over 2. Okay, so this is kind of a play on things that are a little bit more abstract. You've got some more identities here. Let me find exactly where they are. I'm working backwards. So I've got this. Where's my, kind of disoriented here. Right here, the cofunction formula. So you see down here on the cofunction formulas, we've got some things that say like sine of pi over 2 minus theta equals cosine theta. Cosecant of pi over 2 minus theta is equal to secant theta. You've got to find things that look kind of similar. Now, the cofunction identity that I'm looking at is the sine pi over 2 minus theta is equal to cosine theta. Well, look, this is actually not the same. Okay, look, this is theta minus pi over 2. This is pi over 2 minus theta. It's not the same. However, I can manipulate it to look like it. Okay, and so sine is an odd function. Sine theta is an odd function. So that means that the negative sine of, let's see, pi over 2. I don't want to skip a step. I'll show you exactly. We can do the sine of negative, and now I'm factoring out a negative in here. So this is what I have. So the sine of negative pi over 2 minus theta. That's me just factoring out a negative. So I factor out a negative from here. So that makes this negative. I factor out a negative from here. That makes it positive. So a positive pi over 2 minus theta is equal to the negative of sine of pi over 2 minus theta. Why does that help me? Now, these are the same. Well, Mr. Saris, how would I know how to do that? As you see these things happen. So now you've seen me factor something out. I factored out a negative to make it look like the same inside of this cofunction identity. Now you can have an example of a strategy you can look back on. And so what does this mean? Negative sine of pi over 2. So this means that the negative sine of pi over 2 minus theta is equal to the negative cosine theta. Okay? Well, what does that mean? That means that the sine of pi over 2 minus theta is equal to cosine of theta. right? Which means that the negative sine of pi over 2 minus theta, which is this, is equal to negative 0.34. Okay? How did I go from there to there? This is the identity. This is what I wanted. So this is my original. I'm going to box. So this is what I was looking for, right? But this is the same as this. Mr. Sayers, they don't look the same. Remember, that's where I did the little trick. Proofs are about having a little trick, finding something that looks similar and then doing a little trick. I got to admit, that's probably the most difficult example. Let's look at this. Okay. Strategy. Look for known substitutions. Okay, look for known substitutions. Well, look for just a second. I've got sine cubed x, so it says simplify. Sine cubed x plus sine of x times cosine squared of x. Now, hopefully, you get to the point in this chapter where you notice, oh, there's a sine in both of those. I can factor it out. But what have we talked about already that sort of looks like this? We've already talked about sine squared theta plus cosine squared theta. Does this kind of look like that? Yes, it kind of does. I have a cosine squared here. I have a sine cubed here, which at least is sine to a power. Is there a way that I can make my circled expression here look like this? Well, watch. Sine of x times sine squared of x plus cosine squared of x. Look, I factored out a sine from each of these. Factored out a sine from this one, factored out a sine from this one. What does this mean? This is 1. Goal is to simplify. This is equal to 1. So that's a really simple. So sine of x times 1, not equal to 1. You tell me which is simpler. Okay? Obviously, sine of x is simpler. Okay? What did I do there? I looked for something that is a known substitution. I now know Pythagorean identities. I've got to look for those. Okay? Got to look for those. Here's another simplify. Secant x plus 1. I'm going to rewrite this. Secant x plus 1 times secant x minus 1 divided by sine squared of x. Okay, what's my strategy here? Well, do you see any known substitutions? This looks kind of good. That's a sine squared, but I don't have a cosine squared, right? So here's another strategy. Use algebra concepts to simplify. That's 1. 2. 2 is find ways to convert to sine x and cosine x. You want to get to sines and cosines as much as possible. This is already sine. That feels pretty good. Up here, I got a bunch of junk. I got secants. Yeah. Look at what you've got here. If this was x plus 1 times x minus 1, what would you do? Well, you'd see a difference of squares, and this would be x squared minus 1. I'm going to use an algebra concept right here. Secant x plus 1, secant x minus 1 simplifies to secant squared x minus 1 over sine squared x. Mr. Sayers, you said convert to sine and cosine. Look, this is actually really nice. Look at my Pythagorean identities up here. Secant x, so 1 plus tangent squared is equal to secant squared x. Check this out. If secant squared x, or theta, is equal to 1 plus tangent squared theta, then that means that tangent squared theta is equal to secant squared theta minus 1. Well, Mr. Sayers, how would I know that? It's exposure. Okay, it's exposure. You're looking for things that look like this. So actually, this is equal to tangent squared theta over sine squared theta. So this is an alternate version of a Pythagorean identity right here. So anytime you see secant squareds or cosecant squareds or tangent squareds or sine squareds, you can convert those. And I want to get them to sines and cosines. Tangent is closer to sine and cosine. Why? Because tangent squared is actually equal to sine squared theta over cosine squared theta over sine squared theta. I'm mixing up my thetas and my x's here. I'm sorry. And so this is really sine squared theta over cosine squared theta times 1 over sine squared theta. Check out, cancel, cancel, equals 1 over cosine squared theta is equal to secant squared theta. That's it. I don't know what to tell you. That's it. That's all there is. And so what did I do here? I used algebra concepts, recognizing a difference of squares, right? So, a difference of squares possibility, convert it to sine and cosine, and then simplify it. Let's do another one. Here, what do I got? Strategy. I'm not going to tell you yet. I'm going to let you think for a minute. When I'm subtracting fractions, what do I need? 1/4 minus 2/3 equals question mark. What do I need? Common denominators. Common denominators. Common denominators. So what's the common denominator of 1 minus sine x and cosine x? Great question. Well, it's the multiplication of those two. Here's what I'm going to do. Cosine x, 1 minus sine x, times the other denominator, cosine x over cosine x, minus sine x over cosine x, times 1 minus sine x over 1 minus sine x. Okay, I didn't change the value. I'm simply finding a common denominator. Let's look. First one here is cosine squared x. Ooh, I actually really like that, right? Because that's making me think of Pythagorean Theorem, Pythagorean Identities. And this is still whatever it is. I'm going to leave it. Minus, and this is going to be sine x minus sine squared x. Ooh, this is actually really nice. Because now I have a cosine x and a sine squared x in the top. I got to figure out if I can find that Pythagorean identity. So then I've got cosine x times 1 minus sine of x. All right, let's simplify, because remember, this is a whole expression. I got to subtract this whole thing. So cosine squared x minus sine x minus a minus sine squared x plus sine squared x over 1 minus sine of x times cosine of x. What? Look at this. Look at this. Tailor-made for this. Because I can rearrange this, because I'm adding, I've got sine squared x plus cosine squared x minus sine x over 1 minus sine x. Are you getting excited? Because I am. Look at this. This is 1. 1 minus sine x over 1 minus, oh boy. Cancel out, equals 1 over cosine x equals secant of x. What did I do? Find common denominators and then simplify the expressions. 2 more. Find the values of x in the interval 0 to 2 pi. 1 period. That solve cosine cubed x over sine x is equal to cotangent x. I messed up. I gotta erase that. Delete, delete, delete. Cotangent x. Okay, forget about this part so far. Forget about this other part. Let's look at this right quick here. I notice right away, I've got this cosine cubed, makes me think Pythagorean, but my strategy, solve like an equation. Okay, solve like an equation. Well, get sine x, cosine x. That's what I'm going to do. That's the number one strategy. I didn't put it first, but it is number one. Get things in terms of sine and cosine. I see this. I don't like it. So cosine cubed x over sine x is equal to, cotangent is cosine x over sine x. Well, look at what I got here. If I have two things with the same denominator, they're going to cancel. It'd be like 1/2 is equal to x over 2. Okay, so if I multiply by 2, x is equal to 1. So these have the same denominator, so that means that cosine cubed x is equal to cosine of x. I'm solving like an equation. I need all my x on one side. Well, you're like, Mr. Sayers, why don't you just subtract? I can. Or I can divide by cosine of x. Well, I'll divide first. Hold on. Well, let me undo. I'll solve it per usual here. I'll subtract cosine x, and I'll show you the factoring way. Cosine squared x, cosine cubed x minus cosine x is equal to 0. So that means that cosine x times cosine squared minus 1 equals 0. Well, look at this. Look at this. Look at this. Look at this. I've got this cosine squared minus 1. Look at the Pythagorean identity here. Cosine squared plus sine squared equals 1 squared. So if cosine squared theta plus sine squared theta equals 1, then that means that 1 minus cosine squared theta equals sine squared theta. That's not this. We need it the opposite way. So that means that if I factor out a negative, so this would be negative cosine squared theta minus 1 is equal to sine squared theta. So cosine squared theta minus 1 is equal to negative sine squared theta. That's an alternate Pythagorean identity. I'm going to put that in a pink box. Okay. So now, that means that cosine x times minus sine squared x is equal to 0. Well, what does that mean? That means that either cosine of x is equal to 0 or minus sine of x is equal to 0. Well, what is sine squared x is equal to 0? Well, what does that actually mean? That means we go to the unit circle. Where is the cosine equal to 0? Pi over 2 and 3 pi over 2. Okay, that's where my cosine is equal to 0. That's where my sine is equal to 0. Okay, so I'm using a combination of strategies here. Okay, I'm using a combination of strategies to help myself find all of the places where my solve the equation like normal. Let's start at the beginning. Solve the equation like normal. We're just using sines and cosines. You can still subtract the same thing on both sides, still divide by the same thing on both sides. And then I basically have a quadratic sort of thing here where I can say each of the pieces would be equal to 0. And so that's how I'm going to do it. Okay, that's how I'm going to do it. So when I'm looking for my answers in 0 to 2 pi, I'm saying where is my cosine equal to 0? Where is my sine equal to 0 on 0 to 2 pi? Okay, so that's the key. That's my domain. All right, last one. Find the solutions to the trigonometric equation 2 sine squared x plus sine squared x is equal to 1. So 2 sine squared x plus sine x equals 1. Do you see it? I have a term squared plus a term. I can do a u substitution here, which would give me 2u squared plus u equals 1. Quadratic, 2u squared plus u minus 1 equals 0. Okay? So if I factor this, or I think about it, okay, so I've got 2u minus 1 plus 1 and u minus 1. So 2u plus 1, no, that's opposite. Because I've got to have that middle term be a u, so I've got to have plus the 2u minus the u, okay, equal to 0. So you can quadratic formula, you could factor, you could use asterisks, you could use a graph, but something like this you should be able to, at this point, probably look at. If not, you can use asterisks and kind of get that going, which means that either 2u minus 1 is equal to 0 or u plus 1 is equal to 0. So this is either equal to u is a half or u is negative 1. Well, u is actually sine of x, so sine of x is equal to 1/2, or sine of x is equal to negative 1. Well, remember, you have got this unit circle that tells you all of these things. So where is the sine of x equal to a half? Okay, that would be pi over 6. That would be 5 pi over 6. That would be 3 pi over 2. Okay, that's where it's going to be equal to negative 1. Okay, so these two go here, this one goes here, and they haven't really put any restrictions on my domain, so I've got to say pi over 6 plus 2 pi times x, meaning that would be like, so here's pi over 6, and all the way around would be a coterminal angle, so this would be pi over 6 plus 2 pi plus another 2 pi, or so plus 4 pi plus 6 pi dot 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 dot. The way that we say that is pi over 6 plus 2 pi times x, so x could be 1 for 1 revolution, 2 revolutions, 3 revolutions. Or I could have 5 pi over 6 plus 2 pi times x, meaning it's pi over 6, 5 pi over 6, or all the way around again, or all the way around again. 2 pi x is a way to say plus another revolution, because they didn't put restrictions on the domain. Or this 3 pi over 2 plus 2 pi x. So what's my answer? This is for 1 revolution around. This answer here plus these two things gives me all of the answers into infinity for coterminal angles, okay? That's section 1. It can be challenging, okay? And so I need you to stick with it. Trust the process on this, and trust me when I say refer to these strategies, and if you want to, copy and paste those strategies that we talked about through the notes down in this little strategies page. But please, stay with this. You can do this. We're looking for ways to solve these problems that involve using our identity sheet, substituting known values, and algebraic principles. That's what we're going to be working with during these proof problems, okay? Thanks for watching, guys, and we'll see you next time.